Yeah, so those are the 11 modules that are planned to cover in this kind of a training, which yeah, used to be called Introduction to Supercomputing, but it is more introduction on how to use the supercomputers. There are several aspects of using the supercomputers that are not very straightforward and are very different to the way we work on even on our Linux workstations. So that's really what we are going to cover today. Not at all how to program for the supercomputers or yeah, how to develop code, etc. It's more the first impression and the first of all, uh, or at least many of the main aspects on how people work in the supercomputer. So the slides are very nice. This is not my work, so I really find them really nice. So there are some icons there that you need to be aware of, new concepts or some warnings that you need to come back and read again to have them in mind, best practices, etc. So those are the indications in the slides. Oh, so that's, yeah, sorry. So that was basically, I went too fast on this. So I guess, I hope there are not too many questions about the icons, but then 11 topics are, yeah, brief introduction and how to log in. So those are listed. I guess the main, well, all are important, but I guess this part of running jobs and the scheduler is sort of the main part of the training. So I'm going to try to go fast and spend a bit more time on the part of the running jobs and the scheduler. But I guess if you have any questions as I go through, just let me know. I'm usually a slow teacher, so I will try to rush myself. So probably that will still be normal to slow pace. But if for any reason you feel I'm rushing, just let me know, and we can spend some time in some specific slides that I may be jumping fast. Okay. So then that finishes the first presentation. So these are the 4 objectives we all should be paying attention in basically what is the computational performance in a supercomputing, have an idea of, be able to list what are the parts that form a supercomputer, describe the interconnection within the supercomputer, and specifically for Setonix, what are the major hardware specifics for the supercomputer we have here. Again, the icons, and here we go. So so the first concept to know is how fast, basically what is the power, the computational power of the supercomputer. So the idea is to have in mind this kind of operations. So these are the operations that are used to measure the power of the supercomputer. They are called floating point operations, basically sums, subtractions, and multiplications. Those are the floating point operations. This is to challenge you how fast you can do these operations. Probably you are very good in mental maths, but there is a limit. But those are the operations. How many operations of that kind a computer can do? So this floating point operation is what is called a flop. Now supercomputers are in the order of petaflops per second. So a petaflop is 1 times 10 to the 15 operations. And when we are talking of flops, rather than doing this of a plural, is more a petaflop per second. That's what is commonly read as petaflops. It's these quadrillion operations in a second. So it's really impressive still on these days. But we are even on this era, we are even 1,000 times beyond the petaflop. So we are recently in the past year breaking the era towards the exaflops. Still many computers are in the peta, so I guess peta is still a good measure. So if we do one of these floating point operations per second, that I guess would be a reasonable limit for a good mental mathematician. So that means it will take 30,000 years to finish one petaflop of operations. So that's huge. And Setonix has a theoretical capacity of around 43 petaflops, although the real testing is a little bit below that. So it's around, I guess, the 33, or we can round it to the 30 petaflops. That's more realistic operative computer power of Setonix, but we are still, if a computer program is super well done and you are very careful, and theoretically you can reach the 43 petaflops. Recently, in the last supercomputer conference that happened last week, it was released a new list of supercomputers. So the fastest supercomputer in the list is Frontier from the Oak Ridge National Lab in the US. So this one has a capacity of around 1,200 petaflops. So it is breaking it was the first computer to break the limit of, or the wall for the exaflops. So it is 1.1 or 1.2 exaflops of capacity. And that's the only one listed. Another national lab, Argonne, in the US, released recently also their new supercomputer, Aurora. This one reached half exaflops and is number 2. So there is a huge jump between 1 and 2. For Australia, well, Gaudi is around 10 petaflops real capacity. These numbers are real. I mean, they have been measured. It's not their theoretical maximum capacity, although that theoretical capacity is also listed in the rankings of the top 500. So Gaudi went down to number 83, and Setonix went down also in this new list. So Setonix debuted as number 15 for its GPU partition last year, but this year it went down to number 25. So a lot of new supercomputers coming. The real capacity of a Setonix GPU part is, as measured, is 27 petaflops. Although, as you will know, or you may know, Setonix also has a large partition of CPU-only nodes. This one has a capacity. This one has not been listed, but from our measures, it's around 5 petaflops of capacity. So this is Setonix. It is, I guess, a really good thing for us in Australia to have this kind of supercomputers. It's really a world-class supercomputer. Another thing that to mention is that this supercomputer is a HP Cray. You can see there Cray Hewlett Packard. So Hewlett Packard bought the Cray company, which has been doing making supercomputers for a while. So it's now an HP Cray. And these other two, the 1 and 2, are also HP Cray supercomputers. Especially Frontier has a very similar, if not identical, hardware as Setonix. So that gives us, or has given us, some advantage in terms of interaction with these large supercomputing centers, but also for researchers that may have reached the capacity in Setonix and needed more supercomputing power. Normally, those researchers have contacts around the world and doing world-class kind of research. They may have access to these large supercomputers which have the same hardware. So moving their codes to these other big computers, it's much more easier. So in Pawsey, Pawsey is a facility that gives service to research all over Australia and in many research areas. So here are listed the health, agriculture, resources, energy, and astronomy. Astronomy has always been our flag research topic, and we have a specific chunk for some astronomy projects on which the other researchers cannot go to. And we are basically supporting the project of the square kilometer array, but it is not our only topic of research. We basically give service to all kinds of research in Australia, even social sciences, etc. So whatever you want to do, as long as you can prove there is a need for supercomputers, then you may have access to Pawsey. Okay, so the building blocks of a supercomputer. So this slide, I just put this picture because there was another image for all supercomputers here. But anyway, so many parts. So obviously the more important thing are the chips and the GPU cards themselves. And these chips and GPU cards are here in the compute blades. So the blades, this is a schematic of Setonix, or part of Setonix, this HP Cray EX supercomputer. So so the blades are a plate, motherboard, if we can say, here, and there are many blades set in vertical that go into the compute chassis. So each of these blades has 2 nodes on them. So basically there is a direct connection of one node to the other, super fast connection. But then this compute chassis has, once you insert all these blades, has an automatic connection of all these blades together in a fast connection. So that makes this node and this node in the blade, but also the rest of the nodes in these chassis to have a very fast connection with each other. And then they are inserted in the main structure of the computer, and then on the back there is further connection from one set, or if we can say, call it one chassis to the next chassis, etc. So there is also these fast connections now between chassis. And that is super important. That is probably the most important part of what a supercomputer, of what makes a supercomputer, because it's really not the amount of chips or GPU cards or hardware, although that is important, but the idea is how fast they can basically work together. So that's why the connection is, if I can say, the backbone of a supercomputer. And then you have the problem of cooling. So all these pipes move the cooling water, so they distribute water, and then all these red and blue pipes that are meant to be here. There are also, the colors are a bit diffused, but are to indicate cold water coming into basically directly towards the blades. So the blades have a direct connection of heat exchange plates to these hoses, and water comes in and out. So there is one cycle of water that is running all the time here. So the hot water that comes out from the blades then will exchange their heat towards the next cycle of water in this cooling distribution unit that is on the side. And then water goes out from here and goes, in our case, goes to the basement, and there is a third exchange of heat, and that final cycle of water that in that final exchange goes down to the underground. I don't know if you were aware that Pawsey has this underground cooling. So at the end, that final cycle is pumping water from the underground and cooling, exchanging heat in that final cycle, and then that water is pumped back again underground with obviously many safety measures and ecological measures for not affecting the environment. I don't know if you have any questions here, or if I should go forward. This is
no questions so far, Alexis.
Cool. So from that beautiful image, now we have this schematic that is very simplified of the major parts of the supercomputer. So all those blades and chassis are schematized here. Probably, yeah, in this schematic, you should understand each of these yellow squares as one node. So basically, 2 of these will make a blade, and then like 8 of them, it's one of the chassis. So what we are seeing here is one of the chassis mainly. So these are the compute nodes, but then how to interact with them. So there are some other nodes similar to these compute nodes, but serve another purpose and are outside of the supercomputer. If I can say the main supercomputer infrastructure, but are there in the same chassis. But these nodes do not do any kind of compute. So these nodes are meant to basically receive users for connection to the computer. So when you connect to Setonix or to any supercomputer, you land here in these login nodes. You are still away from the compute. Now, the idea is that here you do some preparation of your work. You can interact with the disks. So you save your files, you check your code, and you prepare your scripts for sending them to work in the compute nodes. Once you have done all of that, you send a command that this script is going to run in the compute nodes. So that script is received by the scheduler. So the scheduler also resides in some nodes in the computer, and it's doing all the thinking on when to run that job, how many resources it will need, and find some space for it, and then finally deliver it to the compute nodes. The disks here are mentioned as high performance storage. So the idea is that writing and reading is a very expensive operation and is usually very slow. So what you want to do is that you want the code to run very fast. So then that's why you need a high performance storage that can read and write fast with the compute nodes and do not delay the work that is being done in the compute nodes. And then you have some other nodes that are called data mover nodes. So sometimes for many applications, you need a large amount of data. The files are big, or the simulations are the code that you're running in the compute nodes, and you save the results here. Generate a lot of results, a lot of data. Like, I don't know, imagine you are doing a climate model or a fluid dynamics model around a plane or a turbine, etc. So that those kind of simulations are very detailed and save a lot of results. Then you need to probably move them somewhere else to archive them or to analyze them. So for that, you need the data mover nodes that do not interrupt anything in the login nodes, anything in the compute nodes. So you need these other nodes to also be able to read to the disk and move the data. Could be data coming in for doing the simulations, or releasing your generated data outside. So yeah, login nodes give serve to many users at the same time. Compute nodes is where the computation happens. Scheduler, the scheduler decides where and when to run specific jobs. In the high performance storage, there's also one important thing. We're going to go in detail on this, but this storage is not permanent. So that's why you need to move things in and out. So you cannot keep your results there forever. There's a limit. And the data mover nodes. Okay, so individual compute nodes are similar to a high-end workstation. Yeah, so basically you can buy a workstation with hardware very similar to what we have in the compute nodes. So the performance comes from using many resources together with fast communication. Yeah, so that's what I was telling you. So all these thunders are places where communication is critical. And that is The communication technology that is in the supercomputers could be very, I don't know how to say it, but very high tech and very special and dedicated to supercomputers. So you may not find that in your workstations, if I can say. So this communication, I don't find it that super critical, the communication between the login nodes and the storage. I guess that can be in normal at normal speed, but this communication is critical, and communication among the several compute nodes is critical. This one maybe because sometimes data sets are huge, and to wait days for transferring is not good. So this is the back of Setonix. So I show you the schematics before, basically of the front, and the back was not very clear, but so this is the back of the supercomputer. So all these optic fibers connections between chassis to create a fast connection among all the nodes in the supercomputer is critical. So that's what we call the interconnect. In this case, the technology that is Cray proprietary is the slingshot interconnect. It's very high tech, and the claim is that every node in Setonix is only 3 hops, 3 jumps of cable connections from one node to any other node in the supercomputer. So these hops mean some kind of delay. The more hops you do to reach from one node to the other, the more delay it is. So ideally, you should have a direct connection between one node to any other node, but there are so many nodes that those kind of connections are some kind of impossible. So 3 hops is fine. So the compute nodes, what we are saying here is, and there's another, this is the other part of the supercomputer, is that they can work in parallel. So basically, I don't know, operations in parallel rather than operations in serial one after the other. Just to mention here, so it is not straightforward for a code to run in parallel. So it's not that you create a code and then you just put it in the supercomputer, and the supercomputer will know how to run it in parallel. So there should be an instruction in the code on how to run things in parallel. So I don't know if you think of a matrix multiplication, those happen a lot in the codes. So basically, you prepare the code so that a piece of the multiplications that need to be done for this huge matrix is basically instructed to be performed in one of the nodes, and another piece in the other, and another piece in the other, and then the results shared between them if needed. That's so that's where the fast communications are needed. So when you share the workload and distribute it towards the rest of the nodes, you need this kind of communication. And then when you finally each node finalize the tasks that were indicated for them, they need to sort of merge the results together. So there's another part of communication there. About the storage, mm, okay, so we need this fast storage basically to save the results from the computation or to read the data sets and analyze them. So you need a high throughput of data, either in and out. So this is one important thing. This is a temporary area, so it is not intended to save your data. So um, all nodes can access global storage. Okay, yeah. So basically, yeah, you never know, or well, you can indicate, but usually you don't know which nodes are going to be assigned for your job. So basically, all the nodes in the compute nodes need to have access to this global storage area. Although each of the nodes have some local storage for basically some uh, its own purposes, but uh, that data cannot be read from other nodes. So if data needs to be shared with the other node, needs to be read back again from the local own storage of the node and send it via cable to the via this link shot interconnect to the other node. Um, oops. Yeah. Okay. So those are the schematics, and this is a more larger picture of what is for Setonix. So those were a bit general. This is specifically for Setonix. So we have, besides all the fast communication among Setonix itself, there's this is our fast storage system. I don't know if this number is right, the 15 petabyte, or it has grown a little bit since then. But this is our fast storage system, and the technology it uses is Lustre, and it has two types of disk. So solid state disks, that means chips kind of storage, and also hard drive storage. It's a combination of both. The SSDs are faster, but are yeah, I guess are more expensive and probably a bit unreliable in terms of storing data for longer time. So the idea of the system is that first place to store the data is in the part of the SSDs, and then Lustre itself migrates the data towards the hard disk drives under the hood. So that the fast communication can happen in the SSDs or the super fast, and then the data will still be available in the hard disk drives, which are also fast, but not as fast as the SSDs. Okay, so then we have a backbone of communication channel of 100 gigabits per second, and that connects also the other supercomputers that we may have. So Topaz is now out of our system, has been deprecated, but we will still have some other supercomputers at Pawsey, Ascaraguarla, to give service to the astronomy projects. Then we have some other more permanent storage systems. The one we are going to touch today is Acacia. So basically, when you need to keep data for longer than a month, basically your results, and keep them for the duration of your project, you will need to move data from the Scratch system to Acacia. So there is this S3 interface. So this is an object storage. It's not a typical disk. It's an object storage that uses this S3 technology as the technology developed by Amazon. So you will need to use special protocols to put your data here in a more permanent space if you need so. Banksia is another storage, even more more permanent, if I can say. So data that needs to be kept but doesn't need to be accessed that often can be stored in tape in Banksia. Okay, so Setonix, what we have for Setonix, this is the most important part of Setonix. So we have 1600 CPU nodes. Each of the CPU nodes has 2 chips, AMD chips, Zen 3 Milan. Each of the chips has 64 cores. So then we have 2 chips, we have 128 cores in each of the CPU nodes. And we have 1600 of them. This gives a total of 8 petaflops. This is theoretical capacity of the CPU part. And we have a GPU part, which is the one that is listed in the top 500 list. So only this part is 25th of the world. It has 192 GPU nodes. So each of the GPU nodes has one chip that it's mainly used for controlling the processes. Usually it is not used for computing, but can be used. But anyway, it's there for control mainly. And each of the nodes has four AMD MI 250 cards. One peculiarity of these cards is that each card has, if I can say, 2 GPUs. So usually the GPU part of the cards is called GCD, not GPU. So the full card is called the GPU, and the working part of the cards, which each card has 2, is called GCD. But in this slide, I'm calling, instead of GCD, I'm calling it GPU. So the idea is basically that for all practice terms, each of the cards has 2 GPUs to work with, and we have 8 cards. So at the end, each of the GPU nodes have, in practice, 8 GPUs to be used. Yeah. So 8 GPUs per 192 GPU nodes are the total GPU capacity of Setonix, and that gives a total of 35 petaflops theoretical, and as listed in the top 500, it's around 27 petaflops. Okay, so in this schematic, the interconnect is put in this block, but that's the interconnect of the nodes in Setonix. And that has connection with also our file system. So the performance storage is named Scratch. We have also some Lustre space to save software, and also some other disks to save just the configuration for each user and their home directories, etc. We have 9 login nodes. We have 1 data mover node. We have 3 visualization nodes. Yeah, basically to analyze the data and create all these visualize the results and generate your images and movies. What else? So the backbone of communication and the Acacia storage. So all these parts are important in your workflows. So we need to be aware of all of them. Yeah. So this is one schematic of the interconnect of the nodes in Setonix. It's called, this kind of shape is called a dragonfly slingshot technology. And I guess we can count how many hops we need to move from this node to this node. And in theory, if you follow the lines, you will need only 3 jumps to reach whatever other node that is in the schematics. A little bit more about the nodes. So this is what I told you, all the blades. Each of the blades has okay, yeah, I was probably mistaken. So each of the blades has 2 node cards, but each of the cards has 2 nodes. So yeah, then each of the blades will have 4 nodes. And then all the connection via the switches that connects all the blades, and then all the nodes in this block, and then the rest of the cables. So the information saying here is each cabinet of Setonix has 8 chassis. Each chassis has 8 compute blades connected orthogonally, as I said, and each of the blade has 4 nodes, and each of the nodes has 2 processors, 2 AMD Zen 3 processors with 64 cores each. Okay. So this is a schematic of one of the chips in the compute and the CPU nodes. So basically, there is this memory to which all so the chip is divided in 8 chiplets. So 1, 2, 3, 4, and each of the chiplets has 8 cores. So the idea is that these 8 cores will share this cache. So they share this L3 cache memory. So these chiplets can work together if they need to share data directly with each other. So this is important that the chip, to know that the AMD chips are divided in chiplets. For the GPU nodes, I will show you that each of these chiplets indeed will have a direct connection to each of the GPUs available in the nodes. So basically each chiplet will control each of the GPUs. But on the only CPU only nodes, that is not needed. But anyway, so these are the 64 cores. All these blue squares are the 64 cores of the chip, and all of them have access to a piece of the memory in the node, basically half of the memory in the node. So here's what I was saying. So this purple square is the cache of the chiplet, and each of these cores share the L3 cache, while each of the cores have its own L1 and L2 cache. In terms of the GPUs, this is a blade. So for the GPUs, each blade has only 2 nodes instead of 4. And yeah, each of these one should be the GPUs. So for AMD Instinct GPUs per node, yeah. So this, or at least what we can see is the mark of where the GPUs are. So for MI 250 cards, but each of the M150 cards, as I said, has 2 GCDs or 2 logical GPUs. Okay, so this is an schematic of each of the MI 250 cards, and these are the 2 GCDs. Yeah, with all the compute units around. How many compute units? I don't know if it says here 220 compute units or 880 matrix cores per GCD. Later, I will show you an image of an schematic of the node, of the GPU node. But I guess one very important thing for you to understand is this existence of the 2 GCDs per GPU card. We are going to make use of them later. Cool. So that's basically the main components. Initially, or the presentation was sort of general for sort of any kind of supercomputer, and then specific for Setonix. So we cover the initial concept of the petaflops and what are the logging nodes, the compute nodes, the scheduler, the storage, data mover nodes, interconnect, and a bit of computing parallelism.